Hello everybody, and thanks for watching this video presentation. My name is Ethan Hildebrand, and I'll be asking a question. Should lithium-ion batteries have won the 2019 Chemistry Nobel Prize? The Nobel Prize for Chemistry in 2019 was won by John B. Goodenough, M. Stanley Whittingham, and Akira Yoshino for their development of lithium-ion batteries. The origin of lithium-ion batteries, however, dates back to the 1970s, when Stanley Whittingham started developing them as an alternative to fossil fuels. Over the next nearly half a century, the design for lithium-ion batteries became more and more refined and is now so prevalent in the modern world that the three main researchers were awarded a Nobel Prize. We use lithium-ion batteries in everything from our phones and laptops to storage for renewable energy. But is this worthy of a Nobel Prize? This is the question we will answer by addressing the problem with old batteries, the main principles behind lithium-ion batteries, the chemistry behind them, their applications, and ways they can be developed in the future. We will begin by looking at old batteries. One large issue with old batteries is that they often created large amounts of toxic waste. As opposed to lithium-ion batteries, old batteries typically used a combination of lead acid or nickel-cadmium as the anode and cathode to store energy. Neither of these combinations, when being disposed of, are environmentally friendly and will produce toxic waste. This can create problems when needing to be disposed of because they cannot be thrown away like household trash. Rather, they must be collected at special sites. If discarded improperly, there could be major environmental impacts. Old batteries were also less energy dense than the new lithium-ion ones. This means that to store the same amount of energy as a lithium-ion battery, these batteries needed to be larger in size, resulting in more materials used and more waste produced. It is also a much more pleasant experience for the user if large amounts of energy can be stored or used at once. Old batteries also discharged faster, even when not being used. While discharge is still present in lithium-ion batteries, the internal chemical reactions that cause batteries to discharge when not in use happen more frequently in the lead-acid and nickel-cadmium batteries. Once again, charge retention is appreciated by consumers, but when this discharge is paired with the memory effect, we see a steep drop-off in the lifespan of old batteries. Every battery has a lifespan, but this memory effect refers to the fact that some battery capacities, and therefore lifespans, are shortened by partial charges and discharges of the battery. Lithium-ion batteries do not have this problem, and it is why they are able to be used longer than other types of batteries. The combination of discharging when not in use and the reduced capacity led to a faster overall degradation of lead-acid and nickel-cadmium batteries, which circles back to the point on toxic waste creation and raises major concerns for the environment over time. Additionally, these old batteries had a longer charging time than lithium-ion, which severely limits the number of uses that they would be most effective for. Lithium-ion batteries work by using the principle of electrochemical cells, meaning they have four parts: an anode, a cathode, an electrolyte, and a barrier. In the most basic terms, ions are carried between an anode and a cathode in the battery, which creates free electrons that are stored as power inside the battery to be released later. Now onto the chemistry of lithium-ion batteries. As previously stated, lithium-ion batteries are comprised of four main parts: an anode, a cathode, an electrolyte, and a barrier. We will start with the anode. The anode is typically made of graphite, and while the battery is charging, lithium ions are pulled out of the metal oxides contained in the cathode and pulled into the graphite structure of the anode. During discharge, the opposite is true, meaning that the ions are pulled out of the anode. The cathode is made up of a metal oxide. The most commonly used metal oxides in the cathode are lithium cobalt oxide, lithium manganese oxide, and lithium iron phosphate. The cathode does the opposite of the anode, releasing lithium ions while discharging and accepting lithium ions while charging. The metal ions are involved in a redox reaction, being reduced in the cathode and oxidized in the anode. To get the ions between the two electrodes, the presence of an electrolyte is necessary. The electrolyte used in these batteries is a lithium salt and an organic solvent, which in our case is often lithium hexafluorophosphate dissolved in organic carbonates. Finally, without the presence of a barrier, the anode and cathode would come into contact, creating a short circuit and rendering the battery useless. The barrier in a lithium-ion battery is a porous membrane that divides the electrodes, allowing lithium ions to circulate freely and keeping the free electrons on the positive side of the battery to be used as the charge. The combination of lithium and graphite was chosen for these batteries because of their low electrochemical potential. When paired with any other anode, the electrochemical potential of lithium is higher, meaning the system has to work harder or use more energy to produce the same charge as something with a low electrochemical potential. With the strong effort to eliminate fossil fuels, lithium-ion batteries are finding more and more uses in both consumer and industrial settings. Lithium-ion batteries are the power source of choice for personal electronics such as phones and laptops, and are currently finding their way into larger things, such as the electric vehicle industry. They also find use in storing power from renewable sources, such as wind farms or hydroelectric dams, to name a few. Anywhere that electricity is needed, a charged lithium-ion battery could provide that electricity, be it in space, on Earth, or in the ocean. And applications will only become more prevalent as more and more technology enters the market. The sky is the limit for lithium-ion batteries, but it is not hard to see the areas in which these cells could be improved. As this technology develops further, we can expect to see batteries that are more energy dense, batteries that charge faster, that have a longer life, and are safer than the current ones. If these boxes are checked, the applications for lithium-ion batteries will only continue to expand. Electric vehicles will become more prominent because of their longer ranges and faster charging. Phone battery lives will grow longer, and modern society will need to rely upon non-renewable resources less than we have in centuries. Lithium-ion batteries will certainly be on the forefront of technological advancements for years to come, and as research continues and new developments happen, there is no telling where this area of research could end up. So knowing everything that we now know about how much better lithium-ion batteries are than the old batteries, the main principles of how they work, the chemistry behind them, the wide variety of applications they have, and where their development may go in the future, is it fair that lithium-ion batteries won the Nobel Prize for Chemistry in 2019? The answer seems to be a resounding yes, for all the reasons I just listed. This technology, if developed correctly, will propel us into a world where fossil fuels become a thing of the past, less toxic waste is produced, and life is more pleasant for all. Thank you for your attention and for being a very cooperative audience, and have a good day.